All right, so let's look at the design of portal frame. There are lots of lengths that we need to determine when it comes to member design and section design. So there are segment lengths and effective length (LEF), and there are buckling lengths in terms of LEX and LEY. So let's have a look at what are they and why do we need to work out those lengths and why they're so confusing. So to do that, first of all, let's look at what is because these are associated with a twist restraint. So we need to figure out what is a twist restraint, why do we need to do it, and why do we even to bother it. So first of all, imagine you have a UB. Um, if you're standing on top of that, it's going to bend, right? This beam is going to sag. So you have to think about the behavior of the beam sagging. For a beam like an I beam, it's not going to sag like what you visualizing as a pure vertical sagging, and it is actually not. So what it does is not only it is going to sag, but also it's going to twist and bend sideways. It's just like a if you like bend a ruler, um, it's trying to bend sideways, but plus a little bit of downwards, if that makes sense. All right, because it's so now flexible in terms of the section, because that's something to do with the shear flow with the I section. So the shear flow is coming through, and coming down, and coming down, and coming back up, and again. So this shear flow creates a load path that is trying to twist the beam. So if you can compare that with a hollow section, whereas the shear flow creates a uniform load path that is very consistent in all directions. It doesn't create any twisting flows. So in comparison, the hollow section is much more stable and a much more twist restrained than a I-beam section. So in this case here, this is why we need to think about the twist restraint of this I-beam, because it does happen. So, uh, so understanding the behavior of the I-beam, it twists, it goes sideways, right? It goes sideways. So there is a force when the beam is sagging. There's a force trying to bend, trying to kicking out of the web outside sideways. So there's that force, but cold. That is 2.5% of the critical compression flange force, that is which is the your m star divided by your section depth. So moment divided by your limb arm gives your force kilonewtons. You times by 2.5%, it gives you something kilonewtons force that need to design. So this force is going to be resisted by because it's coupling forces are coming through the top flange and the bottom flange. You're trying to bend, trying to go this way, and the top flange go to the other way around. So there's a coupling force. So that force needs to be resisted by your purlins. So that force coming to here, and how to resist that force. And then normally what you do is you're going to have a welded little cleat here, and you weld another angle right there, and bolted to the top of the purlin. So this is a diagonal here, so the strutting, so they'll call it fly brace. So that fly brace resisting this compression force into the purlins, and the purlins into compression and the tension as well. So there is a coupling force down, up and down. So that is the twist restraint, and also the twist of force that induced by the beam that is bending outwards, bending sideways. All right, so understanding the twist restraint and the twisting force, and we need to next thing is when it comes to design the member, and we need to understand what is the segment length and effective length. First, the segment length is, so basically segment length is where you have those lateral restraints, because the rafter is going to bend, right? So for example, this rafter over here. So where the segment length is to be determined is where the end regions has a full restraint. So to be able to qualify the full restraint, full lateral restraint FL, you would have your top and bottom flanges are restrained. For example, if you have a welded cleat, welded plate like an MEP plate at the end of the both ends of the beams, so that provides a very good flexural lateral restraint, which is the FL. So between those two uh, fixings, solid fixings, so that gives you the segment length. So that is that. So in terms of a long span rafter, normally you would have a MEP plate over here, and at somewhere here you would have a fly brace connecting to the purlins. So that distance is your segment length. All right. Okay. Next is so effective length. So the effective length is actually is something that is reducing your segment length. That it's because the effective length is got a reduction factor called KR. Meaning, if you have a really good restraining really good boundary conditions on your member on your segment, you can reduce your segment length. For example, if you have a MEP at the end and at somewhere here you have a strutting to the purlin, so this length is your segment length, but also when you're talking about effective length, if you have this sort of configuration, your KR, you can use 0.85. So that means your segment length times 0.85 gives you effective length. That is actually smaller. That is about the 15% smaller than your segment length to do your bending analysis, because it just behaves something like a shorter beam. This is it makes sense because when you think about it, when you have a simply supported beam, your bending moment is right here, right? But when you have a fixed moment supported beam, your bending moment is like that. So this bending moment is a lot less than this bending moment. So this is the same thing actually. The effective length LEFF is trying to tell us that if you have really good boundary conditions, I can reduce my segment length to help with my bending capacity design. Okay, move on to the compression buckling length, LEX and LEY. So the buckling length, compression buckling is when you have the axial loads coming into the beam. The beam goes into compression to the full length, to the Z direction. So X direction is major axis and the Y is the minor axis, but you have the Z axis is the longitudinal axis along the beam, along the member. So when you have this compression force into the longitudinal member and your LEX and LEY, and that is actually becomes similar to the bending of the segment. So for example, the LEY bending on when the member is subject to the axial loads, right? So it's going to bend like a sideways, right? It's trying to bend kicking out of the web. So if the LEY length, the effective length in the minor bending axis, it is actually the restraints from the lateral restraints where the where the actual restraints are for FLR. So in this case here, if we will get a flat brace over here, and we have MEP connection here, so this is actually our y direction, in terms of y direction, so which is LEY. But this is actually the same thing as the bending axis. So in this case here, we can also use the KR factor, use 0.85. So which means that if I got really good boundary conditions on both ends of my segment, I can reduce my length, so make my column to be, or my beam to be squashier. That means that I can reduce about 15% of my segment length. So the LEY is actually the segment length and times 0.85. That'll be the same thing with the columns. If I have a columns acting in a axial, loaded in an axial manner, then if I got an MEP over here and I got my really good base connection over here, and then my segment length is going to be the full height of my column, and but because I've got a really good boundary conditions, I can factor by 0.85, so the total height of my column is going to be reduced by 15%. So that helps my column in axial compression. Okay, coming back to LEX. The LEX is the bending about the major axis actually. So this is now this time we're looking at this direction, the bending about the x-axis. So we need to think about what are the restraints to prevent my my beam from buckling. So the actually, if you're looking at the portal frame, that's the clear span here. The only thing that when the beam tries to bend in the major axis is a sag like that, as in it create a sagging. The largest sagging would have been in the middle here. So what's stopping my beam to be sagging into the entire portion? There's nothing. It's only got the column and the restraints. That's the only restraint to my beam in terms of bending in major axis. So in this case here, my LEX is the full length of the rafter span, 36 meters or 38 meters, whatever you specified it. So yeah, that's the LEX. Okay, so that's all of it about segment length and effective length. Effective length is actually affected upon the segment length, and the buckling length in terms of bending about buckling about a major axis and a minor axis. About a major axis is only about the end restraints. What's stopping your member buckling from major axis? It's nothing. It's only the end restraint or the columns or the supports. But in terms of a minor axis, there's bending, buckling through the web region and outer plane region. So what's stopping that? There are many things you can stop that beam, stop that column or beam buckling from the minor axis. You can create your fly braces, and you can do welded cleats to stiffen it. And yeah, there's a lot of things you can do to protect your minor axis of the beam or column. Okay, so yeah, that's all about it. Thanks for watching.